Hello. Today we're going to talk about the basics of steam sterilization and how that relates to immediate use sterilization. Let's just talk a little bit about the different scenarios you're going to see in the OR. Most of the instruments and supplies that are sterilized within the facility is going to go through a terminal process of sterilization, such as what you see pictured here on the right, where the instruments are decontamined, washed. They then go through a washer sterilizer, render them safe to handle. Then the sets are sorted and put back together, instruments checked. Those items are then placed in an instrument container tray that will go into a sterilization container, which you see on this cart in the very back here. That cart then, once that's full, will go into the autoclave. This is one of the large autoclaves that you see back in the back wall there, to be sterilized and then stored for later use. And so those instruments can be carried to the OR, pulled from the shelves, carried to the OR, opened, and used then for a case. Immediate use sterilization, as we see here on the left, is a little bit different. These immediate use sterilizers are typically found in the substerile room in between two ORs or near to connecting to the OR. And this is more for something that we drop during the case or for a set that needs to be quickly re-sterilized. And so the difference here is it's instruments only. They're in open container, nothing in a sterilization container, nothing that is wrapped or pill packed. And so these are in those substeriles, typically next to the room, so that the instruments can be carried into the OR by aseptic technique and then used immediately. So this is not something that we would then store. These would be an open container, thus they would have to go straight to a sterilely draped back table, sterile draped field for use. All right, steam under pressure. First thing, let's ignore everything on the right side of the page here to begin with, and let's look at these three principles here. First, water at sea level will boil at 212 degrees Fahrenheit. So if you're in the mountains up at Denver, then that's going to boil slightly different at a slightly different temperature. When we increase pressure, then we increase the temperature. So to get higher than 212 degrees, the next thing we gotta do is add pressure to it. When we add that and we get a higher temperature, then the third concept, increased temperature equals faster sterilization. So we take steam, which is normally produced at 212 degrees, we add pressure, it increases the temperature, and then we can sterilize faster. So we see here 212 degrees. Normally, our PSI for that is going to be around 14 as far as atmospheric pressure, but on any sort of sterilization that you're using, any sort of container that would have a pressure gauge on it, our gauge pressure would be 0. Now this would be, like I said, at sea level. In order to get 250 degrees, then we've got to get our gauge pressure up to 15 pounds per square inch to be able to produce 250 degrees. If we do that with increased pressure, means increased temperature, means we can sterilize in 15 minutes. If we increase that pressure even further to 27 psi, Then at sea level, that would give us 270 degrees. And if we have 270 degrees, then that allows us to sterilize in as fast as 3 minutes. So the increased pressure increases the temperature, and increased temperature equals faster sterilization. All right, so we've got two different ways in which the autoclave works, and you see immediate use autoclave here on the left, the door and the control panel on the front, but that allows you to see a little bit of the inner workings of it, and this one has an onboard steam generator. And with gravity displacement, these can run both gravity or pre-vac. Now, not all autoclaves are going to be set to run on pre-vac, but they would all be capable of running as a gravity cycle. With gravity, steam enters the chamber, and then due to it being more dense than the air starts to push out of the valve that's in front of the autoclave. And that continues until the autoclave completely fills with steam. That pressure goes up to the 27 psi, 27 to 30, and then creates that temperature of 270 degrees. We're able to sterilize instruments as fast as 3 minutes. Now, sometimes we're going to need to do a little bit different here. For instance, when we're sterilizing a drill system, something that has a lot of pieces and parts, that's hard to get the steam exposure to all those parts. Now we need that steam getting everywhere on the instrumentation in order to sterilize it. So with pre-vac, we're going to first do some pulses of steam and then vacuum. And so what we have is a pulse of steam, pressure goes up, temperature goes up, but not necessarily to the same level that we would on the gravity. And then it is vacuumed out, and we pull a negative pressure. Then we will go through an additional pulse, steam in, temperature goes up, pressure goes up. Then we vacuum out that steam, temperature goes down, pressure is negative at that point. Now this is repeated, typically 3 to 4 pulses, and then we will start the actual sterilization cycle, where we will allow the steam to build up to that 27 psi, 270 degrees, so the chamber completely fills at that point. Now, when it does it at this part of the pre-vac cycle, we've already gone through those conditioning pulses of steam entering and then being vacuumed out, pulling negative. And when we've done that 3-4 times, then when we start the actual sterilization cycle, we get much better penetration. Now, it's worth also noting this is automated with the system, so you don't have to shift it back and forth through this. Once you put it to run, then it will go through this on a preset cycle of the pulses and then the actual sterilization. So once we get to this point, we can actually sterilize a instrument set or drill in 4 minutes. Now there is a lot of additional time that goes into this that will add to that. So let's look at the cycle parameters, and this is what we're going to be verifying on the mechanical readout of an autoclave. And we call it a mechanical readout because most of them are type out or print out on a printout, but in some of the older autoclaves, and I remember seeing some of these, you had a temperature time graph, which was a circular piece of paper covered 24 hours. And when the temperature would go up, the little graph chart would go up, but there wasn't a recording of the pressure. So you did have to monitor and check and make sure that the pressure went up to the indicated point, and then you would check on the graph the temperature and the amount of time. With gravity displacement in an immediate use autoclave, where we're going to be going to that 270 degrees, then we can sterilize in as little as 3 minutes. But now to be 3 minutes, it can only be a few instruments. They should not be touching. It's not a full set by any means. And no instruments with a lumen or a coating. So lumen would be such as a suction tip. So lumen is just a cannula or a hole that runs through the instrument. So suction tips would count for that. So even if you're sterilizing only one suction tip, it would have to go for 10 minutes instead of 3 minutes. Okay? So only a few instruments, no lumens and no coatings. Okay? If we're doing a complete set or even one instrument that has a lumen or a coating, then we're going to have to run it for 10 minutes at 270 degrees. Now, also note here that I give you a range for the pressure, and that's that sea level to Denver variance. So you have a range of 27 to 30 psi in order to get to that 270 degrees. But what we're really wanting is at 270 degrees for the 10 minutes. We do also verify that the pressure was within a normal range. Now for pre-vac, we can do as quick as 3 minutes pre-vac if it's a few instruments, no lumens, no coatings. We really don't do this because the issue with pre-vac is that you've got that time with all those conditioning pulses. And so that extends the complete cycle. So it's not worthwhile. You're not saving time by using pre-vac cycle when you've only got a few instruments, no lumens, and no coatings. So in this case, instead of doing pre-vac, we're going to do regular gravity. Now, if it's like a drill, complete sets, if it's a complete set, we're still going to do it under gravity. If it's a drill, something that we want to assure that it has the all pieces and parts of it sterilized, and drills, for the most part, will be required to do pre-vac. Now, also note here that goes according to the manufacturer standards, and they let the facility know when they purchase a drill or any other piece of instrumentation equipment, how it can be sterilized and how long, what parameters it would have to meet. But most of our drills, if we're doing them for immediate use, they're going to need to be run in a pre-vac cycle, and that's going to be for 4 minutes and typically a dry time of 20 minutes. So we've got all that pulses that go, the conditioning pulses before that 4 minutes, then the 4 minutes, then a 20-minute dry time. So you're looking at about 45 minutes to sterilize a drill system. So keep that in mind. If you need to have a quick turnover, then it's going to take a little while to run this drill. All right, now let's take a quick look at the different types of process monitors. So this is kind of be a little bit more of an introduction to each. I'll show you each one then. Mechanical, now as I said earlier, the mechanical gauges, we used to have to watch for pressure, but now all this is on a printed readout. So we get an actual printed readout that shows the time that the cycle starts, that we can see the temperature reached and the pressure reached. And our ideal here is for every single cycle, somebody needs to verify that those parameters were met. Chemical indicators are placed in the instrument trays, in packs that are being sterilized. There are also external chemical indicators that are used if something's being terminally sterilized for storage, so we can see that it's been through the autoclave run. And these chemical indicators showed that it has been exposed to a sterilant. So for steam sterilization, it just shows that it has been exposed to steam. Now, I'll talk a little bit more. There are some that are a little bit fancier, but these by themselves do not indicate 100% for sure that the items are sterile, but that they have been exposed to the sterilant conditions. Then biological, these are bacillus endospores. Now, if you go back and think about the definition of sterilization, for something to be considered sterile, it must be rendered free of all microorganisms, including spores. So we've got to kill all microorganisms, including endospores, which are the most resilient. And so this challenges that by being a test that we can place in the autoclave to make sure that it is capable of killing spores. And then the Bowie Dick test, or dynamic air removal test, is another type of challenge test. And this one is challenging pre-vac cycles to make sure that it is removing the air sufficiently on a pre-vac cycle. So let's look at each one just a little bit more. Mechanical readouts indicate the time, temperature, and pressure was correctly met. And so with this readout, we'll see stuff such as the cycle count and a summary of what the autoclave was set to run. And then we can see where the chamber was being conditioned. That would be the C's here. And then at the point that it goes above 270 degrees, you can see it's above 27 psi. That's when it starts sterilizing. So at 11:31:47, it started the sterilization, and then it continued to sterilize down to this point where it exhausts. So this is still above 270 degrees and 29 above the 27 psi, so that 27 to 30. So you can see that is at 11:41 and 47. So we went from 11:31:47 to 11:41:47. And for that complete time, it was above 270 degrees. So we look at this column here, and we see that it was above 270 degrees for 10 minutes. And then we can check the third column and see that it stayed above 27 psi for the entire 10 minutes. That also tells you at the end a summary of the cycle. We do need to verify here that the actual readout that it was above the temperature for the proper amount of time and that the pressure was in normal ranges. All right, chemical indicators. Here's a few different examples. There's many, many more. If you've seen wrapped items, the tape has a striping on it that changes color. Here at the bottom, this arrow. This is a tamper evident arrow that goes into a Genesis type brand of sterilization case. So once it has changed color, indicates that it has gone through the sterilization cycle, and this has to be broken when you open it. So it makes sure that the instruments have not been opened prior to the intended time to open it. And so we know that it's not been tampered with because this would be intact within the case or on the outside of the case, and it's broken anytime you open the case. And then we can see that it has been sterilized. Here we see some a little bit fancier indicators, which have to be exposed to the steam a little bit more sufficiently to be able to get into the area of acceptance. And so as long as that line changes color into that area which is considered acceptable, then it has been exposed to steam sufficiently. Here on the bottom, this is the back of a pill pack, and you can see the arrows here are intended to change color when exposed to steam. If this pack was used with ethylene oxide, then this arrows on the bottom would have changed color. So we've got a variety of these different chemical indicators. This very basic one is chemical ink on paper. So it just changes color, does not guarantee sterility, only indicates that it has been exposed. And we verify these all pieces and parts, from internal indicators to the external indicators and internal. Every single item that we open that has been autoclaved in-house, we're going to be checking these. The biological test. These are little test packs, and these are made by 3M, called an A test. These are for a quick readout, pretty nice, fancy type of biological that makes things a little bit easier for us. But these little ampules, I guess you could call them, of sorts, these little plastic containers, at the bottom have endospores. And so these endospores are Geobacillus thermophilus endospores. These are ideal for checking steam sterilization. And so this pack is placed in the autoclave. We run this at least once a day. And then anytime that we are sterilizing implants. Now, when we run this, uh, once it is complete, we let this cool. If you get one with something that's been run, like if you're running some implants that you're going to be using for a case, you'll need to hand this off to the circulator after you get the instruments to your back table. But let it cool just a little bit first before you close that top, and then drop it off to the circulator. But you want it to cool a little bit so it doesn't burn their hands when they take it. Okay. Then it's going to be taken to this A-test incubator, and it will be placed in a little crusher, which crushes a little glass ampule on the inside, and that allows then a growth medium to saturate the Bacillus endospores. Then it's placed in the incubator, and it actually changes color, which you can see visually, but these with the A test give you a readout of a positive or negative. And so you can see this one was positive, and you see that color change to that yellowish. This one was negative after incubating. Now, what we want is negative. Negative is good. Yay, let's give negative a star. Negative is good. That means that the endospores did not come to life and start growing. If it's positive, bad, that means the endospores did survive the sterilization. And once we have it with that growth medium mixed with the endospores, then they started to grow. They became living bacillus and began to grow. And so we know if the autoclave has killed all these endospores and they do not survive. So if the biological is negative, then most likely then the autoclave is sterilizing everything on the inside. And so this is the only thing that gives this really quality assurance that it is sterilizing. Now, I did say we run these daily. They're required at least once a week. Most places run them daily. Sometimes they'll run them every single cycle, as if you get a bad biological, then all instruments that were sterilized Uh, Between that time and the previous goods, biological must be pulled and not used on a case, or if they were used, then the doctor must be notified so that they can then give additional antibiotics to the patient. One more, the Bowie test, also known as a dynamic air removal test or DART. Now, this one is to monitor or challenge that pre-vac process. And so here we're wanting to make sure that we get that really good steam penetration during the pre-vac cycle. We run these once daily. And what we do is we place a challenge pack, and they come in different brands, but this is a good example of what that would look like. Typically, it is a wrapped pack with paper on the inside, and in the middle of that paper is a chemical indicator. So after this has been run, we open the pack and remove that chemical indicator. And what we're looking for is a solid change on that, a solid color change. If you see any splotchy areas in that, any areas that had not changed and that left some splotching in it, then we would not consider that one effective. And so here on the bottom is a comparison between what it looks like before being sterilized. You see the yellow. After being run on pre-vac, it should have that solid gray color and has shown total change without any blotching. And if it's done that, then it was able to satisfactorily pull that steam during the vacuum phases of pre-vac into that package. And so when it was sterilized on a pre-vac, you had good steam penetration. All right. Well, thank you very much. I hope this was helpful and that you enjoyed it.